AP Calculus, Lesson 9.1, Sequences. So, what's a sequence? A sequence is any list of numbers. In this case, I'll draw an arithmetic one or a geometric one. A series is when you add them up. Later on that one, you'll get to it, but not right away. The parts are the initial term, and then you have the terms, and that'll do for now. So here's the definition. Any real valued function with a domain that's a subset of positive numbers is considered a sequence. Think about that for a second. Any real valued function. It's crazy. We could have a finite sequence where we just say it goes from n equals 1 to like 20, or we could have an infinite, n is greater than or equal to 1, just goes on forever and ever. So an example, find the first 6 terms and the 100th term of the sequence a sub n, where is what you got. If you want to pause and try that, go right ahead, but I'm just going to write them out. A1 equals negative 1/2, A2 equals 1/5, A3 equals negative 1/10, A4 equals 1/17, and all we're doing is putting in the numbers and seeing what happens. A5 equals negative 1/26, and A6 equals 1/37. A100 equals 1/10,001. So just an example of how sequences work. Critical thing to notice here is this little piece on top. That'll pop up a lot when we go from negative to positive to negative to positive. Yeah, I'll leave it at that. It's kind of like a yo-yo, kind of like a sine curve, that sort of thing. What kind of sequence is this one? That's actually not really, well, I was going to say arithmetic geometric. We'll come back to that. That's an explicitly defined sequence. The other one is recursively defined. And recursively means what's one of the terms? Okay, the next term, you take that term and you do something to it. So the first 4 terms of this recursive sequence is 4, and then it says take the previous term and add 2. 6, 8, 10, goes on and on. We only ask for 4. Now the problem is if you want the 8th term, and it's defined recursively, you really don't have much of a choice. 12, 14, 16, 18 is your 8th term. And these, of course, are a sub 1 through a sub 4. That's recursive. It's used a lot. You'd be surprised. Seems kind of silly, but no, it's important. So the 2 types of sequences I was going to start talking about too early are arithmetic and geometric. Arithmetic can be written in this form here, and D is called the common difference. We can define a arithmetic sequence recursively. We just say A1 equals whatever, and an plus 1 equals whatever, plus the difference, where n is greater than or equal to 2. It's really not that big a deal. You could also do it for geometric. But here's 2 arithmetic sequences. I'm telling you they're arithmetic. A lot of people say, no, that one on the right is not. So you would just, again, you might want to pause this. I'm just going to write out answers. The difference is 3. The 9th term, after doing a little math, would be 19. Recursively, we would write it a1 equals -5, comma, an equals a1 plus 3, n is greater than or equal to 2. So that's recursively written. And then explicitly written is an equals first term plus the difference times n minus 1. We blast this out a little bit, and we get a sub n equals 3n minus 8, which looks a lot like y equals mx plus b. For this one, we can do all the same work. Just going to write it down. Difference equals ln of 3, a sub 9 equals ln of 13,122. A sub 1 equals ln of 2, comma, a sub n equals a sub 1 plus ln of 3, n is greater than or equal to 2. And last but not least, a sub n, and I'm just writing out the answer here, is ln of 2 times 3 to the n minus 1. You can figure out why, but those are all correct answers. Geometric, we're just multiplying up, and recursive looks the same. The R is called the common ratio. A sub 1 equals something, a sub 2 equals a sub 1 times R, n is greater than or equal to 2. Nothing's really changed. Pardon me, a sub n minus 1. I think I made that mistake before. N minus 1. N minus 1. My bad. Got it. Nope. N minus 1. Because it's not based on just the first term, it's based on whatever the term is before it. Pause if you want. I'm going to just blast out the answers here. R equals -2. A sub 10 equals -512. A sub 1 equals 1. A sub n minus 1. Goodness gracious. A sub n equals a sub n minus 1 times -2. N is greater than or equal to 2. And explicitly, a sub n equals 1 times -2 to the n minus 1. I leave it like that. Most people get rid of a 1. And here we have R equals 10. A sub 10 equals 10 to the 7th. A sub 1 equals 10 to the -2nd. A sub n equals 10 a n minus 1. And is greater than or equal to 2. A sub n equals, again, I wouldn't usually write it like this, but I'll just combine it. 10 times n minus 3. You can figure that one out for yourself. So, give you a couple terms. Geometric sequence, 1, 2, 6, 3, 4, 5, -48. What's the first term, R, and give me an explicit rule? Well, I like to look at gaps. So 6 times something, R to the 3rd, because that's 1, 2, 3 gaps, equals 48. -48. Do the math, R equals -2. Once you have the R equals -2, everything's pretty straightforward from there. This is, of course, -3, and a sub n equals -3 times -2 to the n minus 1. I see people write that a lot of different ways. That's fine with me. Graphing calculator. I'm not going to do this without a calculator. We already seen this one. Go to mode, go down and put it in sequence, function parametric polar sequence, and I change it to dot thick. For whatever reason, we like to put these as dots since they are discrete points. Y equals, we get all this weirdness. Can define things recursively by saying, well, the n min is for just, we're starting at 1. That's always going to be 1. In this case, I did it explicitly. N negative 1 to the n times n minus 1. And my un min is my first term. And it doesn't matter because if I put in 1, I'll get it. So I'm going to leave it blank and see what happens. And we graph it, and we get this. That was really quick, so you've got to play with that with your calculator and see if you can make sense of it. We get something like this. That's just a quick and dirty graph. You should try and do it a little more concretely. But the calculator is a good thing to play with, see if it makes sense. Recursive sequence, again, I just showed it on the calculator. We'll go with the initial term is 4. And then we clear this. I've got to go back real quick to make sure I get it right. It's the previous term plus 2. So we go with this very, very interesting thing. A little trouble seeing. Second 7 u parentheses n minus 1 plus 2. And there it is. We said start at 4, go up by 2. Graph it. We'll get a nice straight line up. Can't see it. Let's change the window on the y from negative 5 to, let's go to 100. See how that works out. Yeah, shows it. Just a straight line going up. So if you ask me to graph this, again, I'd be much more precise, but we're just going off. And some calculus. Let L be a real number. Sequence has a limit as n approaches infinity. If it's getting closer and closer to some number, it stays closer and closer. The difference between the limit and the number is some small number. In our case, we used to say point. I'm not even going to say what we used to say. We just make sure it's a really, really small number, which is not even remotely close to a positive definition. But converges, it converges to L. Doesn't, we just say it diverges. If you go back to unit 2, you can add and subtract and all that nonsense. Go check your notes. But here is a limit, and we can look at this as 2n over n minus 1 over n, or we could just graph it. And that equals 2 minus 1 over n. We say the limit as n goes to infinity of 2 minus 1 over n equals 2. And if we graph it, we'll see that it's getting closer and closer and closer to 2. So here they are. I would play with them, see what happens. We've actually graphed these. This one on the left did this sort of thing and this sort of thing. Well, that's diverges. Even though these numbers get closer and closer to 2 and negative 2, no, 1 and negative 1, since it's bouncing back and forth, it diverges. And this one just went straight up. That also diverges. So you get to do a little review of limits. And then there's sandwich theorem nonsense, which I'll do very, very briefly. It's not on the on the AP exam, so I wouldn't worry about it too much. But we say, show this converges. Well, we know that the absolute value of cosine of x is always less than or equal to 1. It bounces up between 1 and not 1. So we could write down that cosine of n over n has to be less than or equal to cosine of n over absolute value of n. N is always positive. Cosine always goes back and forth between 1 and negative 1. This is going to always be less than 1. That's what that says here and here. And that's just going to be n. So for all integers n is greater than 1, we're looking at basically negative 1 over n is less than or equal to cosine of n over n less than or equal to 1 over n. The limit is cosine of n over n goes out to infinity is going to equal 0. So it's a slightly different way to do the limit than what we did way back in a different chapter. The sandwich theorem makes you think about the absolute value, like you just said. If the limit of something with an absolute value equals 0, then the limit without it is going to equal 0. We just proved that in a very abbreviated way. I apologize for going quite so quickly, but using up a lot of time on this video already. That's it for now. This one's not so bad, so get out there and happy mathing.